So for the forage biomass prediction project that we did, it really centered on the understanding of could we estimate biomass production based on imagery from drones or satellites, and what kind of imagery that would incorporate. Where producers would see a benefit on this is one, just predicting total biomass, so knowing what forage is out in either their hay fields or their pastures prior to harvesting or grazing. And where this comes into play is predicting feedstocks, so before you're on the field, getting a good prediction, as well as playing into grazing plans. So knowing what you're starting with before you head out to the pasture, or managing grazing rotations and grazing management while the summer goes on. And being able to make use of a drone pretty simply, as opposed to conventional methods of collecting, clipping, weighing, and getting your estimate that way. So this technology isn't necessarily novel. There are some agencies and some researchers using NDVI, for example, to predict forage biomass and just plant matter. What we are doing is applying this perhaps in a different way than it has been before, where, for example, forage and hay yields will then be estimated using these images, or even more so on the grazing side, where, as I said, rotations are planned, and stocking rates and stocking densities are planned based on what you're predicting is out in the field, rather than doing clippings and weighing the samples using traditional methods.
So we collected satellite imagery, again using the normalized difference vegetation index to show us the biomass in the fields, and then we also flew it with a drone at about the same time as when the satellites were going over, so we had we're comparing apples to apples. And then we created zone maps out of that to look at where we had really healthy crop, or hay, where it wasn't so good and where it was really bad. And then we sent out field technicians again to do field sampling in those locations. We gave them points in each of the different zones, GPS coordinates to go to and collect some samples and weigh them. So we had a wet weight, as well as then we dried them out and had the dry matter.
We utilized two different sources of imagery from Sentinel-2 satellite. It's a European Space Agency. And we're also using a drone with a multispectral camera here on the smart farm. Utilizing imagery is a pretty common tool. We utilize it on a daily basis to monitor crop conditions on the smart farm. The problem is, without ground sampling, we cannot really detect how many tons per hectare or pounds per acre of grain or green biomass is collected from the field. So for that purpose, we did ground sampling. For the purpose of analysis, we took two different remote sensing information, including satellite imagery and drone imagery. What you see here, it's a satellite imagery from Sentinel-2. So this information was clipped to the field boundary and then used for creating a geospatial map. The same analysis was done with the drone imagery. So as you can see, there are different areas with a higher yield biomass and lower green biomass in the area. And of course, we need to utilize ground sampling to figure out what those vegetation index numbers mean for us. So we identified certain sampling locations in different parts of the field, including low and high biomass zones, and collected them, and then recalculated the total green biomass yield. So here on the left screen, you can see the results of actual harvesting and predicted using satellite imagery and drone imagery. Well, of course, there's slight discrepancy between the results, but overall, they're pretty accurate, pretty close, within 3-4% difference, and we're pretty happy about that accuracy. Surprisingly, we didn't find very much difference in terms of accuracy between drones and satellite imagery. So the results were pretty similar, on average within 3-4% when it comes to the total yield. And same thing when we compared the final results with actual harvested green biomass. That was quite surprising. The results were within 2 or 3% accuracy. So that means our experiment was successful, utilizing some small ground samples and either drone or satellite imagery. We're able to predict the total yield of green biomass and create virtual yield maps for green biomass basically in the middle of the growing season. Because there are many arguments what's better, drone imagery or satellite imagery. Of course, well, each tool should be used for a specific purpose. So satellite imagery, of course, gives way more scalability because one satellite image can cover many thousands of fields across large territories, which makes everything much easier. At the same time, there are several obstacles for utilizing satellite images like cloud coverage. Of course, if we have clouds like we have a lot this year, there will be no clear satellite image. However, drones give us way more flexibility. We can collect imagery on any day when we want. And for that purpose, we can utilize both tools depending on the situation. So the main purpose of that project on green biomass was to utilize satellite or drone imagery and ground sampling to estimate the amount of green biomass growing in the field. This is a very important thing for making on-farm decisions. In the middle of the growing season, we would like to know how much hay can be harvested from the field, or how many pounds per acre of green biomass is growing in the pasture to be able to manage and move the cattle.